the title of the seminar is, and the subject is very close to my heart. So I'll be talking about statistics of irreducible subrepresentations in large tensor products of irreducible modules over simple algebras. And I thought this talk is for 1 hour and a half. So I also added a piece about quantum SL2. So I don't know how it will go. Maybe I'll go over time, or maybe I'll just cut the quantum part. So anyway, the first part about simple algebras, it's based on works with Olga Postnova and Vera Serganova. So the work with Vera Serganova is still unpublished, but I hope it will be published very soon. So, so the plan is the following. First, I'll say a few words about the statistics of invariant tensors in systems with n spin atoms when the number of atoms goes to infinity. So this is the case of the representations of SU2. And then, so this is more or less related to physics. And then more mathematical part will be the second part. That's similar problem, the statistics of irreducible finite dimensional representations in large tensor products of simple modules over simple algebras. And then, as I said, I prepared quantum SL2 piece, but we'll see if we'll have time for this. Okay, so here's the physical problem. Suppose we have n atoms of spin 1/2. As we all know, the space of states is C2 to the n. And strictly speaking, when I write it C2 to the n, the tensor product is ordered. So secretly, it means that I enumerated atoms 1, 2, 3, 4, and I wrote this tensor product in the order of enumeration. But of course, all these orders are irrelevant. So that's just some subtlety. But I want to emphasize that I'm not talking about spin chains. N is not the length of a spin chain. I mean, it might look like a spin chain because it's a long tensor product, but it's just a system of n atoms. So here, n is not the length of the spin chain. It's just a number of atoms, and n goes to infinity is not a thermodynamical limit in the sense of large volume limit on a spin chain. It's a thermodynamical limit in the sense that the number of atoms goes to infinity. So then SU2 acts on C2 to the n diagonally in this way. So usual thing. So then tensor product of two-dimensional irreducible representations of SU2, it decomposes into irreducible modules of SU2. So these are the irreducible SU2 modules of spin L over 2. And then these are the multiplicity spaces. But according to Schur-Weil duality, we also know that these multiplicity spaces are irreducible representations of the symmetric group. And for this reason or for the other, there are probably 100 combinatorial reasons why the multiplicities are given by the difference of binomial coefficients. One of these combinatorial reasons I will discuss later on. When I'll discuss the connection with lattice path. Okay, so far we know the decomposition of this tensor product. And then let's consider the uniform distribution. I call it Boltzmann distribution, but this is really Boltzmann distribution at large, sort of infinite temperature. So it's just a uniform distribution on the space of invariant tensors. So the probability of L is given by this number. So it's the uniform distribution on all representations, and I shouldn't call it uniform distribution. It really, what is this is a Plancherel measure. So in the most general setting, originally this appeared in the setting of representations of symmetric group, but you can introduce this probabilistic measure on any space like this. Suppose that you have a space, it doesn't even have to be a representation space, which you write as a direct sum of certain fixed vector spaces with some multiplicities. Then you can introduce the probability of occurring of this specific vector space in this direct sum. Just define it like by this number. And in case of SLN, this is the in case of SN, this is the Plancherel distribution. Okay, so the question is, what happens as n goes to infinity? And here is the theorem that goes back, I think it goes back to Kirov, 1970s, late 70s. Or maybe even earlier, that the probability of this irreducible representation converges in probability to this distribution. So here, 1 over the square root of n, this is like dA, and so the correct statement is not about the pointwise convergence of this function. By this function, I mean this function. The correct statement is that if you have some test function g, then its expectation value as n goes to infinity converges to the expectation value of this function with respect to this continuous measure. And of course, if you look carefully at this measure, you will recognize the invariant measure, Gaussian measure on the dual space to SO3, quotient by the coadjoint action of the group. In other words, it's the natural measure on the space of SO3 orbits in the corresponding space to dual space to the Lie algebra. So this theorem, it follows immediately from the explicit formula for the multiplicity in terms of binomial coefficients and from the Stirling formula. Okay, so that's an example of such statistics. For finite n, it's the Plancherel measure, and then miraculously it has this continuum limit. So then let's consider something more interesting from the physical point of view. Let's consider Boltzmann distribution. So it's a quantum system. So it's, strictly speaking, it's a quantum density matrix corresponding to the quantum Boltzmann distribution in the presence of magnetic field. In this case, well, let's see if I wrote it correctly. No. So in this case, the distribution is e to the minus 1 over Boltzmann constant and temperature, the Hamiltonian of the system, plus magnetic field times the projection of the spin. So now this formula is the limit when h is fixed. The temperature goes to infinity, and h, which is the magnetic field over the temperature, is also fixed. So in other words, you consider strong magnetic fields, large temperatures, so that whatever the dynamics, quantum dynamics you had in the system, it sort of it disappears because the temperatures are so high that they're much bigger than the characteristic energies of the system. What is left? Only the ratio of magnetic fields to the let me put minus here, magnetic field to the temperature. So this is the physical meaning of this distribution. Obviously, it's a density matrix. It's non-negative. Its trace is 1, so it gives a state, kind of thermodynamic state on our system. And yes, so for example, if you have an observable which is SU2 invariant, it acts on the space of our system. It acts on the space of states in this way. Remember this decomposition into irreducible representations. So because it commutes with SU2, so it acts trivially on the representations of SU2, on irreducible representations of SU2 by Schur's lemma. And it acts only non-trivially only on the multiplicity spaces. In other words, in our case, on corresponding representations of the symmetric group. So then the expectation value of this observable on our thermodynamic state is given by this formula. And then using this structure, you can compute it as the classical probability that that is written here. And then the quantum uniform density matrix on the multiplicity space. So this measure, this is a classical probability. This is not quantum anymore. It's a measure on the symmetry types of tensors that occur here, and it's induced by the quantum density matrix that I just described. So this is the physical meaning of this. So, and yeah, in general, if you have any SU2 module, which is a direct sum of irreducibles, you can still have this classical probability of the same origin on the induced by the quantum density matrix. And you should always think of this character measure. So the name of this is character measure. And it's a deformation of the Plancherel measure. Deformation parameter is h. Okay, so we know the asymptotical behavior of the Plancherel measure. Now we want to know the asymptotical behavior of the measure of characters, of the character measure, in the same limit as n goes to infinity. But now we have one parameter, so we have more interesting cases. So the question is how this distribution behave when n goes to infinity. First, let's consider the most natural case. Magnetic field is fixed, n goes to infinity. So then the answer immediately follows from the asymptotical formula for the binomial coefficients. So this is basically Stirling. Formula plus the formula for the character, for the irreducible character, we all know it. It's the simplest version of the Weil character formula. And then you do the computations and you got the following result. So now the limiting distribution now is different. It's a Gaussian distribution supported at Oh. Okay. Supported here. So at this point, and then there is a Gaussian distribution here at the scale of the square root of m. So this width is square root of m. And a is the rescaled Gaussian variable. It's very similar to the, when you do the coin tossing, you also have this distribution centered at probability, half time one side, half time the other side, but then there is a Gaussian distribution around this point, and the random variable is exactly this a. Okay, and then probability for all other L that are proportional to n but not equal to eta is exponentially small. So this is the situation of so-called large deviations. That's how this phenomenon is known in probability theory, when the probability measure is concentrated at some point, and then it's exponentially small or super exponentially small in other areas. Okay, so this is the answer for the fixed magnetic field, and then yeah, these are the, in this answer there is k, there is s, and there is eta. And on the next page I define what is k, s, and eta. So s is this. So this, in probability theory, this is called the large deviation rate function, and g is just this function, and then k is the second derivative of s, and eta is the point where the this function is maximal. So in particular, this means that, I mean, this is how I should have formulated this result in the first place, that this probability measure is concentrated at this point, and on functions that are supported on sort of in the square root neighborhood of this point, it converges to the to this Gaussian measure. And remember that as if h is 0, then the convergence was to the measure a squared e to the minus a squared. This is not a Gaussian measure. It's sort of similar to Gaussian measure, but it's not. It's a Gaussian measure on invariant functions on SO3 star. And this is Gaussian measure on the Euclidean space. Okay. So, but now we can think of sort of more tricky limits when you increase the number of particles and you decrease the magnetic field. It turns out that there is a scaling limit like this. So in this case, random variable b occur as this renormalization of L. L is the spin, and the magnetic field should be rescaled as n goes to infinity as 1 over the square root of n. X, some numerical constant. I mean, it's a fixed constant, like combination of 2's and pi's, it doesn't matter. So the result is the following statement. If you consider the expectation value of a test function supported near 0, in these rescaled variables, then the expectation value converges to this expectation value, this continuous expectation value. You see, the probability measure is again different. And of course, as u goes to 0, in other words, when the magnetic field is really 0, it's not like 1 over the square root of m. This measure turns into b squared e to the minus b squared over 2 dB, which is exactly the limit of Plancherel. So there is this special case. But then why did we assume that 0 is a special case and infinity is not a special case? So let's look at what happens at infinity, and indeed something interesting happens. So if we consider the limit h to infinity and m to infinity with this combination fixed,
我这边也听不见 I cannot hear anything.
Okay, it seems it's Nicolai's network. Let's wait for him.
We consider the case of strong magnetic fields when h goes to infinity, so that the magnetic field pushes the system into its largest possible spin. So then if you do the computations, you will see that you have to, so this limit is the following. This combination should be fixed, and then if this combination is fixed, then you have this one parameter, leftover parameter theta, and the distribution becomes Poisson distribution. You have the largest spin, then the spin by 2 smaller, then another spin. So on the space of the spins that are just next to the largest spin, you have this discrete Poisson distribution. So this is the behavior of the system for large magnetic fields. Okay, so this was the physics. So I want to emphasize this is not about spin chains, it's about spin systems with n atoms. Okay, so now associated, so some combinatorics. With this decompositions of the tensor product, we can associate a lattice walk. So let's V1 be spin 1/2 representation of SU2, two-dimensional space. VL be L plus 1 dimensional space, spin L over 2 representation of SU2. And then this decomposition is well known to everyone. So if you take this tensor product, it's isomorphic to the direct sum of two irreducible representations with multiplicity 1. And so this means that the multiplicity, this number, the multiplicity of representations of subrepresentation VL in the tensor product of n C2s of n V1, it's given. Oh, now I can see terrible mistake. Change the view too. Okay. So you see, you have a lattice, And then when you take the tensor product, so this is n equals 0. So this is just C2. The multiplicity of C2 is C2. So then you do the first step. Sorry, this is the one-dimensional representation. N equals 0. N equals 1. There is so this is C2. And then if you multiply it by C2, you can go either one-to-one-dimensional representation, L equals 0. Here L equals 1, here L equals 2, or you go to the two-dimensional representation. Then if you multiply one-dimensional representation by C2, you can go only to C2. If you multiply a three-dimensional representation by C2, you can go either to two-dimensional or to four-dimensional, and so on. So, but you always constrained by the fact that the highest weight of the representation is non-negative. So you can only move your lattice path on the right side. And so that's the reason why MLN is the number of red paths. The paths that stay on the right from 0. And of course, it's a simple combinatorial exercise that if you allow all walks, you know, with probability 1/2, you go to the left, with probability 1/2, you go to the right, without this constraint that the walks cannot cross this wall. Then the number of walks is equal to this binomial coefficient. And then it's a simple exercise to check that the reflection principle, which says that if you want to count path only red path, all you have to do is it follows immediately from here. It follows immediately from here. So you just move the number of yellow paths to the right, and the number of yellow paths, of course, is just the number of paths from this point. All paths from this point to our point. And so that's the reason why you have this formula. That's one way to prove this formula. Okay.
Sorry,
So
may I ask
now-
a question?
Yeah.
So how do you get this subtraction? So I understand that so you have the total paths, which is the total number of states, and then the red paths are the highest weight states. But how do you interpret this subtraction?
So this is MLN, and the yellow path, they maybe it's a bad drawing, but yellow path they allow to cross. So yellow paths, they don't have to stay there. So they're completely free to move around.
So the definition of the yellow paths is the set of all possible paths, right?
It's the set of all possible paths that are originated from here,
Yes.
from this point. So this number is n binomial coefficient n over 2 minus 1. So you just start your random walk at the new place.
Okay, I see.
Mm-hmm.
So if I think in terms of a light cone, then it's like it's you know in terms of a space time, then it's like the past somehow, the past light cone or something, right?
Oof. I never thought about it in this way, but
And what is this reflection principle?
That's the reflection principle. That's the reflection principle that that you can split all your random walks from the origin to this, from here to here, into two groups. One group that doesn't cross the green line, and the other group is which is originated at this new lower point, but which can cross the green line. So you have a simple combinatorial formula for the total number of paths that can cross the line. You have a simple combinatorial formula for the paths that can cross the line but originated at a different point. And the reflection principle is that you can move one of these numbers to the right with the minus sign, and you get the formula for the number of red paths.
Right, I see.
I mean, yeah. Go ahead.
What is the meaning of this this green line? Those two green lines. You have two green lines. It's like the axis.
This is n. This is where it stops. So you take C2 to the n. That's the length of the path.
And the vertical one is.
And the vertical one is that you. So this is L equals 0, and then this one is L equals -1, and you don't want to allow your path to go to L equals -1, so you put a wall between 0 and -1.
Right.
So
thank you.
Okay. So there were some questions in the audience. Maybe I made a mistake. Yes. Maybe it's n-1 here. Sorry. I explained the idea, but the numbers can vary in the first part.
No, but
Yeah.
I think it's actually n choose, right? Because if you think if I think of it in terms of spin chain, it's n choose m minus n choose m minus 1. If I remember the formula for the multiplicity.
Anyway, so
yeah.
Here's the homework: n versus n-1. So I'm sure you can do it. So that's the idea of the reflection principle, and the outcome of this reflection principle is that so before the reflection principle, the structure of the random walk of this lattice walk give you the number of the multiplicity as the number of the lattice walks constrained to the right side. And then the reflection principle gives you the expression for this number in terms of the binomial coefficients. So there are two statements here. Okay. So then one can rederive the results that I explained before using Markov chains, using lattice walks with some probability distribution with which probability you go to the left, with which probability you go to the right. So far, I didn't describe, they were not random, they were just combinatorial walks. So now let's put some probabilities to the events of going to the left or going to the right. So, and the idea is the following, that if we'll assign some probabilities to going to the left or going to the right, then at the end of the day, we will have the probability distribution on the endpoints of this path. So it's just the probability will be the product of these probabilities with appropriate multiplicities. So in other words, if we have a Markov chain defined on this combinatorial data, then this Markov chain will induce the some probability distribution at the level n over here. And so the statement is that the uniform distribution, I don't know why I call it uniform distribution here. It's not the uniform, it's the Plancherel distribution. And I don't know why I used the German way of spelling Plancherel. He was French. Okay, distribution on invariant tensors correspond to Plancherel Markov chain, and by definition, so here is the definition of this Markov chain. The probability, transition probabilities from L to, so we have here L, and then we move to either to L minus 1 to L plus 1, but now we move to these positions with these probabilities, which is simply the ratio of the dimensions. And it's very easy to check that this is a Markov chain, that the sum of probabilities is 1. It follows from the formula for the dimensions. So yes, and then if L is large enough, if L goes to infinity, you can see that the probabilities, these transition probabilities, they converge to 1/2, which means that, okay, so that's the property, and I'll give the interpretation a couple of slides later. So then, if H is fixed, then you can define the instead of dimensions, you can put characters. They still sum up to 1 by the property of characters. And then as L goes to infinity, the distribution is different now. Going to from L to L plus 1 is more probable than from L to L minus 1. So then if we will draw the picture of this Markov process, it's a random process. So our path, if H is bigger than 0, it converges to some place here. And because for large n, so somewhere from here, maybe, considering that after this place L will be large enough, so this will be Markov chain with constant probabilities with the constant drift. So drifting to the right will be uniformly more probable than anything else, and drifting to the right with the slope that is determined by these probabilities. And so from here, geometrically, you can easily find the place where this measure will be concentrated. And then it's a simple exercise with Markov chains to rediscover the same probability distribution around this point. But now, if H is 0, if it's Plancherel, it goes straight down because, you know, the probability is going to the left or going to the right is the same, but it's just this path, this bounce from the wall, so it goes down. And it's not Gaussian because it bounces from the wall. It's like it's deformed Gaussian. And this is where a squared e to the minus a squared over 2 appears. And then if H is small enough, 1 over the square root of n, the path is pushed a little bit to the right, but not significantly, not enough to go macroscopically to the right. So it's still, say, if you do computer simulations, you will still see something like this. But then if H goes to infinity, then 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 almost surely you go to the right, which means that there will be macroscopical stretches of the path where it goes to the right, to the right, to the right. And then in one place, it jumps to the left. And then there is another macroscopical stretch, and then it jumps here. And that's the Poisson process. So this is the story for SL2. Any questions about SL2? Okay, so I'm running over time. I'm sorry, and I did less than half of my slides. I don't know what to do. Should I rush through?
It's okay. I think you can go to 12 o'clock, so you still have plenty of time. So
no, sorry. I didn't start at 10, so I still have time. Oh,
yeah.
Yeah, okay, good. Okay, so so now mathematical problem, which still may have some physical flavor, but sort of it has more mathematical flavor than physical. So now let G be a simple algebra. Think of SLN, fix a Cartan subalgebra, diagonal matrices. Let's fix an irreducible finite dimensional representation with the highest weight nu. For SLN, nu can be regarded as a Young diagram, well, some equivalence class of Young diagrams where you count only the differences between the length of rows. The Young diagram itself would be GLN, which is not a big difference. But anyway, so now consider nth tensor power of V nu. Because the Lie algebra is simple, we know that it decomposes into the direct sum of finite dimensional irreducible G modules with some multiplicities. So fix an element H in the Cartan. And by the Cartan, I mean it's a real Cartan. So here for SLN, this would be real numbers HI such that the sum is 0. Then we can define the character measure on those representations on lambdas which occur in the decomposition of V nu to the n. So it's just the multiplicity times the character of the irreducible subrepresentation divided by the total character. It's clear that these are non-negative numbers. It's clear that the sum of these numbers is 1, so it's a probability distribution. So while character formula gives us the formula for the characters, so that's a good news. But these numbers are quite complicated. So so the question, can we compute the limiting distribution as n goes to infinity for any given nu, for any given representation V nu? And so this question has some history. So these types of problems started with the work of Kerov, Vershik, Logan, and Shep, 1977. So these works were really about the Plancherel measure on the symmetric group in the limit n goes to infinity. Then Kerov in 1986, sorry, I made a mistake. This SL2 result, it's a particular case of this result, and so it's 1986. So he studied the Plancherel measure for these representations of SLN. Then Philippe Bien in 1993, he computed the asymptotic of multiplicities in the limit as n goes to infinity when V is irreducible for any G. Then Tate and Zeldich in 2004, they gave a kind of lattice path interpretation of these multiplicities, and well, they rederived this result by Bien in this way. So then with Olga Postnova in 2019, we studied character measure for generic magnetic fields. So this is the analog of H greater than 0, strictly greater than 0. So H alpha, so for example, for SLN, this would be HI is not equal to HJ for any I and J. So then this work with Serganova, which we just have to write, it's all done. So we computed the character measures for all magnetic fields, in particular when some H alphas are 0. So it's the analog of H equals 0 for SL2. But because there are more components in the magnetic field, so you can have some HIs are equal to HJ, some are different, and so on. So it's a bit more complicated. So for SL3, it means that there is this Plancherel measure that goes back to Zeldich and Tate and Zeldich. So this measure for generic H that we did with Olga, and then what this paper, what is done in this paper is that we studied the distributions here, and then of course there are these special cases of large H and small h, so they are very similar to SL2. So how to compute this asymptotic? Well, asymptotic of the probability of the character measure. First, one should compute the asymptotic of the multiplicities. And for this, the best thing to do is to use the orthogonality of characters. So this is a beautiful result that probably goes back to Hermann Weyl, and I don't know exactly the history. So anyway, so it's a well-known fact that if G is a compact Lie group, if you take the invariant measure on G, Haar measure on G, then the result is this, and when you pass from integration over G to integration over Cartan, there is this factor, that's the absolute value of the square of the Weyl denominator. So this is the denominator in the Weyl formula. And then from here, you immediately have the integral formula for the multiplicity. And all you have to do is you have to compute the asymptotical behavior of this integral using the steepest descent method. And the result is this. So this formula. So let's just reflect on this. So it's the factor n to the rank over 2. Then that's the dependence on n, pre-exponential, then square root of the determinant of the matrix of the second derivative that I'll introduce soon. So then, yeah, this point x also will be introduced down below, and the S function is introduced here. So it's the minimum over y of this particular combination of the logarithm of the character of our irreducible representation, and you have to subtract yc. The character is log concave, so there is only one minimum, and that minimum is just, you take the derivative of this function, and that gives you the equation for the minimum. It's impossible to solve this explicitly, but there is only one solution because of this log concavity property. So we have the S function, we have X, and then K is the matrix of second derivatives of S, and Xi, as I already introduced above, the weight lambda is n times Xi. Lambda is the highest weight. So we have this formula. Nu is fixed, n goes to infinity, Xi is fixed. Okay, so Xi is fixed, and somewhere secretly there is an assumption that it's generic. But for this result, we only need generic ones. So then we use the results of step 1 to compute the asymptotical behavior of the probability measure. So we use this result plus the while character formula to compute the asymptotical behavior. So if H is generic, this is what we did with Olga. So the result is the following. This probability measure converges to the Gaussian distribution supported at point eta. So the probability is decaying exponentially when, remember, Xi is lambda over m. So it's so if Xi is not equal to eta, eta is this very special point, which is the minimizer of this function. Then it's decaying exponentially. If Xi is equal to eta, then around this point you have the random variable b at the scale of square root of n, which is distributed Gaussian, and and this matrix K is the same matrix as above. It's the matrix of second derivatives of Xi at the point eta, and eta is the maximizer of this expression, where S is the minimum of this function. It's equal to this expression if X is the solution. So it's not very explicit, but it's almost explicit. And then the theorem is that the probability converges to this Gaussian distribution. Okay, so then I assume that Xi is generic there. So now, so H is generic. So now this is the result with Postnova and Serganova. So now let's assume that H is on a wall of the principal Weil chamber. In other words, this means that there exists a Lie subalgebra such that, say, positive roots of this Lie subalgebra G0 is a subset of positive roots of G. In other words, positive roots of G is the union of positive roots of G0 plus some other roots. And then being on the wall of the principal Weil chamber means that the components H alpha, when alpha is a positive root of this Lie subalgebra, are 0, and the others are positive. So for SL3, this would be either sitting here or sitting here. So now let R0 be, and so for SL3, G0 obviously is SL2. So now let R0 be the rank of G0. So then we have the following asymptotical behavior. You know, this is this is correct. Yes, so then if you look at the Weil character formula, for large so lambda for large highest weights, so lambda is proportional to n, but now your highest weight is going along the wall of the principal Weil chamber. So then it's not difficult to see that there is this asymptotical behavior of the character formula. So you have the exponents coming from the you remember that in the Weil formula the sum in the numerator is over the Weil group. So this is the contribution when the Weil element is equal to the identity. So this and this whole exponent. And then the other well, anyway, so it's a little bit long story, but that's the answer. So then the if lambda is behaving like this, where a is a random variable, let's see, now I have to make sure that it's correct. So yes. So now A is a random variable when you go inside of the chamber, and B is a random variable on the wall of the chamber. So so this is the definition of A and B. And then it's a little bit involved. So then V lambda is an irreducible G module, but now you consider the restriction of V lambda to G0. Remember that now we have a Lie subalgebra G0. H on G0 is 0. So this is the definition of the number X. That's the number that I didn't want to explain. Anyway, so that's the number X. And then the theorem is the following, that the probability distribution in lambda converges to n to the r over 2, then these factors and these factors, which means that it's the product of probability distributions in B and A, independent. It turns out that they're independent random variables. So I just want to remind for SL3. So this is the point eta, and then from the point eta we have the fluctuations that go inside of the Weil chamber and that stay on the boundary of the Weil chamber. It turns out that they are independent random variables. So the A's are distributed as on the dual space to the Lie algebra G0, and the B's are distributed in the Gaussian way. So, and then there are extreme cases when H is very near the Weyl chamber, when H is going to infinity. H is going to infinity. So you see for SL3, for example, the set of weights that can occur in the tensor product, it's bounded. So it's bounded by some kind of wall over here. So when H is increasing, then the process will stay near the boundary. Okay, I think I rushed through, but I finished the Lie algebra part. So now there is quantized universal helping algebras at roots of unity. Should we leave it to the next time, or should I go on?
Oh, I guess we can arrange another meeting next time. So yeah, either next week or whenever it's convenient for you.
So
is it okay?
Yeah, that's fine. It's about for half an hour, but I'm afraid that people are already tired from the Lie algebras.
Yeah, it's a lot to absorb, and I guess people may have some questions.
Okay, so let's move it. Let's move the quantum SL2 to the next time.
Okay, sounds good. Let me stop the